Okay, so let's take a look at problem 38 from chapter 19. So in this problem we are given a PV diagram here, and a number of processes are depicted on the diagram, and they're asking questions about these processes. So we have a gas that's taken from A to C along the curved path, figure 32. The work done by the gas is minus 35 joules, and the heat added to gas is minus 63 joules. Along path ABC, the work done is minus 54 joules, and they're asking a number of questions. So let me just first put the information we have on whiteboard, and then we're going to look at each of these questions in succession and see if we can figure those out. So we have a PV diagram. So this is problem 38. A PV diagram. And something like this. Right, so let me check. A, B, C, D. B, C, D as follows, and we have this curve thing here. There are also arrows on the other curves, but it doesn't really matter for our purposes. So this is a PV diagram, and they are giving us a number of values. So the work done by the gas along the path A to C, so WAC, is minus 35 joules. The heat along the same path, QAC, is minus 63 joules. And they're also saying along path ABC, the work done is minus 54 joules. So ABC is minus 54 joules. Is that right? Yeah. So this shows that how you go from A to C makes a difference from work, and that makes sense because work is not a state function. Unlike internal energy, work and heat are not state functions, so they depend on the path that you go from one point to the other. Right. So what can we calculate from these before we start our manipulations? Let's take a look and see what we can calculate from these. So from these two, so since delta E internal is just Q minus W, delta E from A to C is going to be Q from A to C minus W from A to C. So this is something we can calculate. This is minus 63 minus 35, whatever this is, joules. And this is work done over the path ABC, so A, B to C. But the work done, so this is equal to the work done from A to B plus work done from B to C. Right, this is what this means. And the work done over A to B is some number, but work done from B to C is just 0. Because the volume does not change, you're not doing any work. This is just going to be 0. So this number given here is actually equal to work done from A to B over here. Yeah? And now let's take a look at what they're asking and see if we can just, by using these numbers we have, we can make the calculations. So what is the Q for path ABC? So Q ABC. Now this by first law of thermodynamics is just going to be W ABC plus delta E ABC. Let's not write internal here, it's just too much clutter. And well, this thing here, this is internal energy, it's a state function, so this is simply just A times C, and this WABC is just something that is given, so this is just WABC, a given number, plus delta E from A to C, right, because it's a state function. How you go from A to C does not matter, and this is also something you can calculate from the given values, and you just substitute the values in and you get your answer. Right? So for part B, let's here perhaps. If PC is half PB, what is W for path CDA? So PC is half PB, and they're asking for W for path CDA, WCDA. Now this is WC to D to A. First of all, the work done over D to A is just 0, so this is just work done from C to D, right? And then, because this is work done from C to D, if you compare this to the work done from B to A, because the pressure of this line is half the pressure of this line, the work done over this volume change must be half the work done over this volume change, right? The work done in a PV diagram is just the area under the curve, and obviously if you just move this twice the distance from the x-axis, you're going to get twice the area under the curve, and so the work done from C to D must be just half the work done from B to A. So this is half the work done from B to A, which is equal to minus the half work done from A to B. So it makes a difference whether you're going from this way or that way, right? Increasing the volume or decreasing the volume, you do opposite work in those cases. And so going from C to D is something like going from B to A. Then we just revert the initial and final states and pick up a negative sign. And this is something we already know. That's one of the givens in the problem. Okay? And then for part C, let's take a look what they're asking. What is Q for path CDA? So Q for CDA. So again, by using the first law of thermodynamics, I can rewrite this. Okay, just go over there. So this is going to be W CDA plus delta E CDA. And WCDA is just the work done over C to D to A. Again, the work done from D to A is 0. So this is just WCA. Plus, this is a state function, so it doesn't matter that I'm actually going through D. It's just going to be delta E CA. And that is just negative this. And this is just negative that. Right? So this is actually QCA, which is just negative QAC, which is one of the things that's given in the problem. Okay, so just by first law of thermodynamics, this corresponds to QCA, and then if I change the initial and final state, I just pick up a negative sign. All right, and so for part D, what is E int A minus E int C? So let's try to fit this in here. E int A minus E int C. Okay, so this is the change between two states, a change in internal energy between two states. So it's either this or the opposite. Right? So what is this? So this is the change in internal energy as you go from A to C. So is this E int A minus E int C, or the other way around, E int C minus E int A? Well, when you're doing this, what you normally do is you just subtract the final value from the initial value, right? Just to give a very simple example, let's say you're going from 3 to 5, your delta is just 2, and this is of course equal to the final value minus the initial value, right? So the same deal here. This thing is some change in a quantity, so it's just the final value minus the initial value. So this is the final value C, E int C minus E int A, right? So this thing is just the opposite of that. So this is going to be delta E from C to A, which is just minus delta E from A to C, right? So this is a good question, because they are asking you about the meaning of these symbols that you're manipulating. So if you're manipulating them mindlessly, you're going to have some difficulty with this one. And then if E int D minus E int C is 12 joules, what's Q for path DA? Okay, let's see if you can fit this in here. E int D, is that? Yeah, minus E int C is something. This is given, but what is this? Well, by virtue of this derivation over there, this is delta E CD, going from C to D. They're asking for Q for path DA. So Q DA. Now I want to relate this to this somehow, and well, one way to do that is to write this as, so this is from going from D to A. I can just say I'm going from D to A, I can go from D to C to A, right? So DC plus QCA. And now using first law of thermodynamics, I can write this in two ways. So this is going to be just delta E DC plus work done DC plus delta E CA plus work done CA. Okay? So obviously these are not related to each other. Okay? Now this we know, delta ECA, we just calculated over there. Work done or CA is something given, right? It's just negative this. So this we know, we can calculate. Work done DC, this thing we must have calculated somewhere. Yep, it's here. It's just negative of this, but it is already calculated. So this is done. The change in internal energy DC is actually what is given in this part of the problem. Or again, it's just a negative of this, but this is also given. So you plug numbers in of everything previously you found, and one quantity that's given in this part of the problem, and you can get your answer. Right. So as you see, this kind of problem has a lot of manipulation, and just you need to just think about these things. But it's designed in such a way that it just solves itself. It's just one step follows from the other. Right. So in real life, obviously, it's not going to be this simple. Okay. So for the next problem, we have the same diagram, but this time the numbers are obviously different, the ratios are different, and so on and so forth. So we have in the process of taking gas from state A to C along curved path shown in this figure. 85 joule of heat leaves the system and 55 joules of work is done on the system. So here they're not seemingly being as helpful as in the previous program, but they are, because at the very end they're actually just giving you all the numbers. So we can just read this as QAC is minus 85 joules and WAC is minus 55 joules. And then determine change in they're again asking a number of things, and I'm going to just put everything we have and try to manipulate it that way. And first let me just gain some space by erasing things. Now I apologize for the lighting. I was actually going to record this quite a bit earlier, but I actually solved it with D here and B here, and I noticed it too late. So yeah. Okay, so what are the givens in the problem? Let's take a look. So for everything, they are given QAC. QAC is minus 85 joules, and then WAC is minus 55 joules. C is minus 55 joules. Determine the change in internal energy E int A minus E int C. Okay, so E int A minus E int C. Now, if you look at the previous problem, you already know that this is delta E CA, which is just minus delta E AC, which is just minus QAC minus WAC. Right? So these two things are given, so you can calculate the change in internal energy as you go from A to C, which is just negative of the internal energy as you go from C to A, which is what this is. Okay, so for part B, when the gas is taken along the path CDA, the work done by the gas is W38 joules. So WCDA is given 38 joules. Okay. How much heat is added to the gas in the process CDA? QCDA, they are asking for this. Or is that it? Is this so? Yeah, this is tricky. You need to go back and look at the definition of is it positive when it's added to the gas, or when it's taken from the gas? I think it's positive when it's added to the gas, so they're really asking for QCDA rather than minus QCDA. And so how would we do this? We know something about A and C, so let's divide this into two parts. let's first write this using first law of thermodynamics. So this is going to be W CdA plus delta E CdA. Now, excuse me. So this is the work done as you go from C to D to A, C to D to A. Now, as with the previous problem, from D to A there is no work done, so this is just work done from C to D, and from C to D, plus this is internal energy, so this is just L delta E. See, actually no, I can just keep this because this is given, right? It's 38 joules, but this is a state function, so it doesn't matter how you go from C to A. The CdA is same as CA, and this is given, right? This is something we already calculated in the first part, so you plug numbers in and you get your QCdA, right? So for part C, if PA is 2.2 PD, how much work is done by the gas in the process ABC? So, oh, sorry, this is part C. What's this? PA is 2.2 PD. PA is 2.2 PD. What's the work done by the gas in the process ABC? Again, you need to look up the definition, whether this is positive when work is done by the gas or work is done on the gas. I think in this case it's negative, right? But I'm just going to calculate this ABC, and it's up to you to figure out whether this is the work done on the gas or negative of it. Done by the gas or just negative of this. Okay? So how would you calculate WABC? So WABC work done as you go from A to B to C. Again, from B to C, this is nothing. So this is just work done from A to B. All right. And this work done from A to B is 2.2 times the work done as you go from D to C, right? Because this curve is just 2.2 times higher than this one. The area under it is just going to be larger by a factor of 2.2 as well. So this work A to B is 2.2 times work C to D. It's 2.2 work C to D. And now this is work C to D to A, but this is just work C to D. Right, and you have your answers. Because this is given in the previous part, you can calculate work from A to B. Right? No, I made a mistake. So going from A to B is the same as going from D to C. D to C, and this is actually negative 2.2 times the work done as you go from C to D, which is a positive number. Right? So this should turn out to be a negative number. You're decreasing the volume. But yeah, apart from that, the numerical value is calculated that way. Now for part D, what is Q for pad ABC? Q for pad ABC. So you go from here to here to here. Again, I'm going to write this using first law of thermodynamics as W ABC plus delta E ABC, and this thing WABC is the work from A to B to C, which is just work from A to B. Work from A to B, which is something we calculated over here, and this delta E ABC, because delta E internal energy is a state function, is the same as delta E AC. See? And it is something we calculated here, right? It's just a negative of whatever this is, so this thing here. So, or something that's given in part A. We didn't really calculate it, but something given in part A. So you just again plug numbers in and find your answer this way. So for part E, if E int A minus E int B is 15 joules, what's Q for the process BC? And then they give you a very helpful summary. So this is E int A minus E int B, which we now know is delta E BA, right? So there was a more detailed discussion of this in the previous problem, so you can just go back and watch that one. So this is given to be 15 joules. 15 joules, and they're asking for Q for process BC. So we are given something about BA, and they're asking for something about BC. So yeah, one way to do this is just to write this as QBA plus QAC. Right, and then now we can relate this to delta EBA. So this is going to be delta E BA plus WBA plus delta E AC plus WAC. Okay. This is a bit problematic because this is not well defined. Right? It depends on how you go from A to C. Is this given? Oh, it is given. Okay. All right. So that one is given, and this one is it's already calculated here. So this is given. This is something we already calculated. This one is given in this part of the problem, and WBA is calculated over here. Okay? So all of these are numbers that were calculated before. You'll need to look them up and plug them in and just carry out some addition and subtraction, and you're going to get your answer. So as you see, for these problems, it's just algebraic manipulation, and as I said, the problem almost solves itself, and in real life it's not as clear as sometimes you're going to have incomplete information. For example, you'll need to go back and make additional measurements and things like that. But this is just general physics 3. So yeah, this is the kind of problem that we are going to encounter. Okay, thank you.